All right, welcome back. I am here to finish out chapter 6. So we have just a little bit left that I didn't get to. Last time we had ended by talking about Lineweaver-Burke plots, right? Lineweaver-Burke plots being very, very convenient, simple to make plots that can help us more easily ascertain the values of Vmax and Km. All right. The one last concept I forgot to mention directly relating to Michaelis-Menten kinetics in that form is something called the turnover number. Turnover number is a very simple little definition. It's defined as the number of moles of substrate that can react per second per mole of enzyme. So every second you have a mole of enzyme. How many moles of substrate can that mole of enzyme convert to product within that 1 second? And so, as you might expect, the bigger the turnover number, the more efficient the enzyme is, right? This is referred to by the term kcat, K sub cat. Kcat is going to equal the Vmax over the total enzyme concentration. That's it. All right. So the higher the turnover number, the more efficient the enzyme. And you can see from looking at your chart, again, this one's not showing up very well here, but if you look on a computer at your PowerPoint, as I'm doing right now, there's a pretty wide range of efficiencies within enzymes, right? We've said that generally speaking, they tend to be more efficient than their non-enzymatic counterparts, like metals or acid catalysts or something like that. But even within the body, there's a wide range. The one that we looked at earlier, catalase, is probably one of the most efficient enzymes. It's got a turnover number of 4 times 10 to the 7th power. That's crazy. That basically means every second a mole of catalase can convert about 40 million substrates into product. So it could handle 40 million moles of H2O2 and convert it into water and molecular oxygen within that 1 second period. So very, very efficient. All the way down there, we see chymotrypsin is several order of magnitudes less efficient. And then lysozyme is actually pretty slow. It's the one that's responsible for breaking down bacterial cell wall polysaccharides, sugars, etc. Right? So when you see turnover number, that's what it's doing. It's referring to it's basically a mathematical determination of the efficiency of an enzyme. Right? Okay, so the last thing I want to talk about is something called inhibitors, right? Well, what do you think an inhibitor is? You can probably tell from the name, right? An inhibitor is something that slows the progress or stops the progress of something, just generally speaking. Well, enzymes can have inhibitors. An inhibitor of an enzyme inhibitor is going to be something that is going to bind to the enzyme and either slow down its reactivity or slow down its function or completely shut it off, right? Depending on the nature of the inhibitor and the nature of the enzyme. If we go back here, back to the Lineweaver-Burke, which I just realized I don't... Oh, okay. This slide here, this one has the photo. Again, look on a real computer or your book, you'll see the whole thing. You see it's got a certain shape and it's got a certain slope. We're going to take a look at a couple of different types of inhibitors, and we're going to see that these inhibitors are going to have certain very regular effects on Lineweaver-Burke plots, and thus the determination of Km and or Vmax. All right? All right, so let's define them. There's basically 2 broad categories of inhibitors. These are competitive inhibitors and non-competitive inhibitors, right? A competitive inhibitor is going to be one that directly competes with the substrate to get to the binding site of the enzyme. So literally, in a competitive inhibitor, you have this molecule and the substrate trying to get to the same spot. Okay, so let's say we have an enzyme here, and I'll just do this. I don't know. I'm really bad at doing these little drawings. So let's say here's our enzyme, and then this right here is our active site. That's where your substrate is going to bind. All right, so you might have your substrate right here, and it wants to go right here, right? And that's what triggers actual action of the enzyme and conversion of the product. However, you might have this other little thing. I'm making this up on the fly, so you might have this other little thing over here, right? Not perfect, not exactly the same shape as your substrate, but pretty similar, right? Especially down here, wherever it's going to be actively attaching to your active site. This would be an inhibitor, specifically a competitive inhibitor. So these two guys are both fighting for this spot. And obviously, if the competitive inhibitor gets to that spot before the substrate, that spot is blocked and the substrate can't get in there anymore. All right? So that is a competitive inhibitor. And then you also have a non-competitive inhibitor. This is going to be an inhibitor that still binds to the enzyme, but it doesn't bind at the active site. So it's not going for the same thing that your substrate is going to do. Basically what it does, it sort of almost acts like an on-off switch, right? It's going to bind to the enzyme at some other spot, and that's going to cause the enzyme to sort of shift arrangement, shift conformations a little bit so that it doesn't fit your substrate very well. All right, so going back to the whiteboard, all right, I'll see if I can remember how to draw this. If I don't, then I don't. I don't know. Okay, that's our enzyme. Okay, and so actually, let me adjust this a little bit. Nope. Meant to draw it the other way. Okay, so here's our enzyme, and here's the active site right here. All right, over here, we have our substrate that's supposed to come in and bind at that active site. But also over here, you have this. This is our non-competitive inhibitor. All right, so here's what happens. If a non-competitive inhibitor comes in, it can bind at a place other than the active site. Let's say it bound right there. All right, so here it is, bound in its little spot. And what it does is, when it binds, it causes the protein to shift and rearrange a little bit so that the active site doesn't look the same anymore. Right, so I went from having like a little, I don't know, a little rectangle here and sort of like a little broad V shape here to kind of having these little spiky teeth-like portions, right? And now your enzyme doesn't fit it so well anymore, right? So it's not inhibiting it by directly competing for the same active site, but it just binds elsewhere to change that active site so it's no longer favorable. All right. Each one of these can have an effect on kinetics, the rate of reaction. What does it do at a very basic level? Well, it slows it down, right? Yeah, and that's intuitive, right? You hear inhibitor. If it inhibits, that means it's going to make it go slower. It's not going to be as efficient. However, competitive versus non-competitive will do this in slightly different ways. All right. So, if you look at a Lineweaver-Burke plot, almost all of this picture got put in here, but not all of it. So again, look at your full picture. There are very regular patterns that we can see. All right, let's start off with competitive inhibitors. All right, so the bullet points are the Vmax will remain unchanged, the Km will increase, the slope of the Lineweaver-Burke plot becomes steeper. All right. Here's the difference in shapes, right? The no inhibitor line is exhibited with blue. Basically one portion or one equivalent of inhibitor has been added in the green. And you see that line gets steeper. And we added two equivalents in sort of the reddish purple line there. And you can see the slope gets even steeper. Mathematically, we can tell that the Vmax is going to remain unchanged though, right? It's still going to get to the same velocity, maximum velocity, excuse me. How can you tell? By looking at the Lineweaver-Burke? Because no matter what, all three of these lines cross the y-axis at the same point. The y-intercept is the same. And we said the y-intercept was equal to the inverse of Vmax. So if they all cross the y-axis at the same point, that means that there is no effect on the maximum velocity by adding a competitive inhibitor. However, we said that the Km increases, right? Remember, the Km was defined as the amount of the concentration of substrate required to get to half of your Vmax. And you see this does change, right? As we keep adding inhibitors, since the slope is getting steeper, you get larger values of -1 over Km, or the x-intercept, right? It keeps on climbing as you keep adding competitive inhibitor. And that makes sense at a very basic level because intuitively, since competitive and non-competitive inhibitors are competing for the same spot as a substrate, a lot of it's a numbers game, right? You have to keep dumping more and more substrate in there to overcome the numbers of the inhibitor and get the substrate in those active sites, right? So you can still get to the same, eventually you can still get to the same action and reaction velocity. You just got to have a whole lot more substrate to get there. That means, mathematically, that the Km is going to increase. All right? It's a little bit different with non-competitive. All right? With non-competitive, with regard to the Km and the Vmax, these are flip-flopped. The Km is going to remain unchanged, but the Vmax itself is going to decrease. No matter what, though, the slope of your Lineweaver-Burke plot is going to get steeper. So, again, look at your PowerPoint on a computer or in the book at this photo, and you can see, just like last time, the slope does get steeper with increasing inhibitor. However, they no longer cross the y-axis at the same points like we did with the competitive inhibitor, right? Since they cross at different points, that means your Vmaxes are going to be different. As you add inhibitor, the slope gets steeper, and your y-intercept is higher up on the y-axis. That translates to a lower Vmax. However, if you look at the x-intercept now, you'll see that all lines, inhibitor or no, will hit the y-axis at the same point, right? The x-intercept is going to be exactly the same no matter how much inhibitor that you add. That means the Km stays the same, right? So in a nutshell, non-competitive inhibitor can never get to as fast a reaction velocity as something with a competitive inhibitor. However, and with a competitive inhibitor, you got to add a lot more substrate concentration to get to 1/2 Vmax, whereas it ends up being the same with non-competitive. And this last bit here, this is actually just sort of an interesting applied example. It is outdated. I will freely tell you that because, like I said, I did this about 11, 12 years ago. But it's also worth talking. It's also worth discussing because you can actually get an idea for how we can use inhibitors strategically to have important biological, medical applications, right? This one involves AIDS, acquired immune deficiency syndrome, which I'm sure you've heard of. It's a very well-known condition. Really started to become prominently well-known back in probably the 1970s and 1980s. If you weren't around during then, and I don't think you were because you're too young for that, it was a really, really big deal. Really, really, there was a lot of worldwide panic about it. It wasn't a pandemic like, certainly like, COVID. I forgot the name of COVID for a second. But it also pretty much carried a death sentence. AIDS is a condition that will basically eat up or chew through your immune system, and the actual AIDS actually doesn't kill you, but since it sort of immobilizes or destroys your immune system, that means you're much more prone to other infections. So a lot of AIDS patients would die of pneumonia and other types of things like that. AIDS is caused by the human immunodeficiency virus, which is HIV for short. And to this date, there is no known cure for it, no known absolute cure, although there have been reports, I think, of a couple of people who have taken certain medications, had certain treatments that have reported almost kind of quote-unquote being cured or having no HIV viral loads in tests. So that's kind of to be determined, I think, but there's no absolute cure for this. And like I said, it's been proven for a while to carry a death sentence. You will have a shortened life with this. However, as more and more research was done for HIV treatments, there have been remedies that have been found. There's I can tell you a couple of famous people that have HIV, that are HIV positive. Magic Johnson, former basketball star for the Los Angeles Lakers, was probably the most prominent, has probably been the most prominent person to be diagnosed with being HIV positive. He was diagnosed, I was I think a sophomore in high school. So that would be probably like, this is making me feel old, over 30 years ago or so right now. He's actually doing very well. He has still to this day never developed full-blown AIDS. He's just HIV positive means you basically are carrying, you have the HIV virus in you. You're not defined as actually having AIDS until the action of the HIV is prominent enough to cause certain symptoms and test results. So he's never actually developed full-blown AIDS. Charlie Sheen, the actor, has also in recent years, come out as being HIV positive, and there's several others as well. Why does Magic Johnson not develop AIDS after all this time? Well, part of the answer, a large part of the answer is he's very, very wealthy and has been able to afford over the years the ever-changing cocktails of drugs that have to be taken to sort of slow down, combat the progression of HIV. And I say ever-evolving cocktail. Number one, it's a cocktail because usually when you're doing AIDS treatments, it's not just like a one magic pill, there's one magic thing that you have to stop. There's very complex metabolic processes that go into the action of HIV and its replication and the formation of new viruses. So the more places that you can target, the more efficiently you can fight it. It's like fighting a battle, right? Instead of just coming straight on, you want to attack from several different vantage points. So that's why cocktails of drugs are usually given to HIV positive people, and each of those drugs does a different thing. It's ever evolving because HIV is a highly adaptable virus. It mutates a lot. So if you're, just giving one type of treatment that does one thing, it can quickly adapt and mutate itself to where that drug is no longer effective, right? So that's one of the things that makes HIV treatment so tricky, is because its ability to mutate so quickly and become so adaptable to treatments. So this is just one example of the many different types of treatments that have been given for HIV. This drug was called Amprenavir, and you can see the structure of it in the photo. Amprenavir is specifically designed to address a specific enzyme in the HIV replication process. That's called HIV protease. HIV protease. Proteases, by the way, proteases are classes of enzymes that basically sort of cut up, or I guess you could say digest in air quotes, large protein chains, right? They cut them up. They cut large protein chains up into smaller pieces. And that's what this does. HIV protease does this to large proteins to give them smaller chunks that they can use to combine with their genetic material to make a new HIV virus. Basically, in an HIV virus, you have the genetic material surrounded by this sort of protective protein shell or coat. So basically what it's doing, HIV protease, is cutting up some proteins to get the chunks to make this viral coating for it to protect its genetic material, right? And Amprenavir is a competitive inhibitor for this. So instead of the proteins binding to HIV protease and then them getting cleaved, the Amprenavir can bind on HIV protease in its place. So it's a competitive inhibitor. And again, I'm not expecting you to know the structure of this or anything. It's just kind of cool to look at. This bottom one here, again, look at your book. The ribbon model, that's going to be the actual structure of the enzyme. And then Amprenavir can settle nicely into its active site. Amprenavir is actually outdated now. Like I said, this is old, and AIDS treatment or HIV treatments are ever evolving. So Amprenavir has been discontinued, and a better version took its place. It's called Darunavir. It's also a protease inhibitor. It's more efficient than Amprenavir, and also it has fewer side effects. So that's the protease inhibitor of choice now. But just one of many different types of treatments that typically go into the cocktail of treating HIV. But a lot of those cocktails, drugs in that cocktail, those cocktails, are enzyme inhibitors of some sort, either competitive or non-competitive. This is just one example. All right, that's it. That finishes up Chapter 6. Next time, I'll be coming at you with Chapter 7, the second enzymes chapter. All right, have a good one. Talk to you later. Bye-bye.